Human language is messy. It is inherently fluid, full of subtle nuances, sarcasm, and unspoken context that swirls and expands depending on who is talking and who is listening. Computers, on the other hand, only understand numbers. They operate in a rigid, binary universe of ones and zeros, where that kind of organic ambiguity does not compute. This disconnect creates the semantic gap. It is a barrier that prevents machines from making sense of the mountains of unstructured emails, contracts, and research papers generated by global industries every day. For a machine to act as an effective enterprise assistant, it first needs a system that can translate our organic language into a mathematical reality. Early attempts to bridge this gap relied on a method called TF-IDF, which stands for Term Frequency Inverse Document Frequency. It operated by counting words. If a document contained the word apple 10 times, the system would tally up those occurrences and conclude that the document was likely about fruit or technology. There is a flaw in this logic. Knowing a word appears frequently does not mean the machine understands what an apple is, how it tastes, or how it relates to an orchard. Counting frequency is strictly statistical observation. It is a way of keeping score that falls short of capturing the meaning behind the words. Word embeddings shift language from a list of symbols to a spatial model. This technique translates individual words into long arrays of numbers, known as vectors. By treating these arrays of numbers as coordinates, we can plot words into a high-dimensional mathematical space. In this space, physical distance reflects semantic similarity. Concepts with related meanings, like apple and orange, are positioned close together, while unrelated concepts like car remain isolated. The geometry also encodes relational logic. If you draw a path from man to king, applying that same mathematical direction to the word woman lands on the point for queen. While we are looking at a 3D model, real embedding models scale this up to hundreds or thousands of dimensions to capture the various ways words relate to one another. This mapping transforms abstract concepts into navigable geometry that a computer can process. Evolutionary steps like word-to-vec improved this by learning from relationships within local context windows, the words immediately surrounding a target. Word-to-vec utilizes two primary methods: continuous bag of words, which predicts a target word based on its neighbors, and skipgram, which predicts the neighbors based on the target. Another approach, GLOVE, maps relationships by analyzing how often words appear together across an entire corpus of text, rather than just local windows. These models advanced the field, but they shared a critical limitation. They assigned one permanent fixed coordinate to every word in their vocabulary. Because human language is fluid, assigning a static, rigid coordinate to words that change meaning based on their use creates errors in real-world applications. Think about the word bank. In a static model, the edge of a river and a financial institution are forced to share the same mathematical location. The transformer architecture addressed this. This is the design underlying current large language models. Transformers use attention mechanisms to evaluate an entire sentence simultaneously. This creates contextual embeddings, where a word's numerical representation dynamically shifts based on the text surrounding it. Because the model can adjust these coordinates on the fly, it can distinguish between different uses of the same term, resolving the ambiguity of a sentence before generating a response. These contextual embeddings now drive enterprise workflows. They allow systems to extract names from contracts, cluster related documents, and perform semantic searches that find information based on meaning rather than keywords. To apply this to sensitive data, Treecapital developed Anven. It is a sovereign AI model designed to run within a private firewall, focused on high-precision, deterministic logic. Anven utilizes late fusion multimodal processing. It does not treat text and images as separate systems. Instead, it projects visual and textual tokens into the same unified vector space. This allows for specialization without a full retrain. As shown here, quantized low-rank adaptation, or QLoRA, injects specific industry logic into the data stream, working alongside the frozen pre-trained weights of the transformer block. This combination of a shared vector space and targeted fine-tuning allows a general model to function as a specialized analytical reasoning engine. To keep responses grounded in fact, Anven integrates with vector databases using Retrieval Augmented Generation, or RAG. RAG converts proprietary documents into vector embeddings. When a user asks a question, the system runs a similarity search to find the grounded context in the company's own data before an answer is generated. Word embeddings provide the mathematical structure required to turn the messy, chaotic nature of human language into the navigable data needed to power global